Good evening, everyone. I'm Professor Catherine Godson. I'm from the School of Medicine in University College Dublin, and I also serve as the Science Secretary for the Royal Irish Academy. So it's my great pleasure to welcome you to this year's Hamilton Lecture. The lecture is organised by the Royal Irish Academy with the generous support of the Irish Times and IBEC. So each year, the Royal Irish Academy celebrates Hamilton Day to commemorate William Rowan Hamilton's groundbreaking discovery of Quaternion algebra, which he discovered in 1843. So our day of celebration includes an award ceremony to recognise the most gifted third-level mathematics students in their penultimate year of undergraduate studies in Ireland, and I'm glad to see that many of them are here this evening. A masterclass and a Hamilton lecture, both given by an internationally renowned mathematician. This year, we're really honoured by the presence of Professor Caroline Series, FRS, our speaker for this evening. So, Professor Series is Emeritus Professor of Mathematics at the University of Warwick. So, on behalf of the Academy, I'd like to welcome you and thank you very much for honouring us with this lecture this evening. I'd also like to welcome our audience. We have a small and appropriately socially distanced audience from Trinity here in the Burke Theatre. So thank you very much for coming along this evening. And I know we'll have people joining us from all over Ireland and indeed from around the globe on YouTube. So again, you're all very welcome. I'm now going to hand you over to our chair for this evening's lecture, member of the Royal Irish Academy, Professor Martin Matthew. Martin is Professor of Mathematics at Queen's University Belfast, as well as being a member of the Academy and of the Academy's Physical, Chemical and Mathematical Sciences Committee. His research area is that part of pure mathematics called functional analysis, and he's a world authority on the theory of local multiplier algebras. He's also currently editor of the journal Mathematical Proceedings of the Royal Irish Academy. So over to you, Martin, and before I hand over to Martin, I want to thank Caroline again for her presence, and also thank the Academy staff for organising and coordinating today's hybrid events, because as we can all appreciate, that is not without its challenges. So thank you very much to Teresa and her team. Okay, thanks, Martin, over to you.
Thank you, Professor Godson. And good evening, everyone, here in the auditorium and everywhere in the world behind your screens. I heard about 500 people signed up for this, and many more will probably join. It's my great pleasure to chair this year's Hamilton Lecture tonight, and as you heard, you're all very welcome to ask questions afterwards in the audience, and if you're online, then you can go to slido.com, and there you just put in Hamilton Day, and then you can already, during the lecture, put in your questions, and they will be monitored and passed on to us after the lecture. So now to this evening's speaker. I am very fortunate to have known Professor Caroline Series for a number of years, first through our work in the London Mathematical Society. She was the president of the LMS 2017 to 2019, and more recently with the European Mathematical Society, in particular through the Council. Originally from Oxford, Caroline received her undergraduate degree from Somerville College, Oxford, and then went to Harvard University with a Kennedy Scholarship. She obtained her PhD from Harvard in 1976 under the supervision of George W. Mackey, and then she moved on to UC Berkeley and back to England to Newnham College in Cambridge. Since 1978, Caroline has been at the University of Warwick, where she became professor in 1992, and she's still at Warwick as an emeritus professor. Caroline's early research focused on the connection between the geometry of hyperbolic surfaces and chaotic motion. Her more recent work is largely about the geometry of three-dimensional hyperbolic manifolds and their associated fractal limit sets. She will probably show you her book that she co-authored with David Mumford and David Wright, Indra's Pearls. And I think you see the cover up here with us, which was published by Cambridge University Press a little while ago. Among her numerous awards and honors, I mention her Junior Whitehead Prize by the London Mathematical Society in 1987. She was an invited speaker at the ICM in Berkeley in 1986. She received the Senior Anne Bennett Prize from the London Mathematical Society in 2014, and in 2016 she was elected Fellow of the Royal Society. Now this year, again from the LMS together with the IMA, she received the David Crichton Medal. While at Warwick, she supervised 12 PhD students, and throughout her career, Caroline has taken a leading role in encouraging women mathematicians. In 2014, she was the first vice chair of the International Mathematical Union Committee for Women in Mathematics. I'm really excited to have Professor Series here at Trinity College as this year's Hamilton speaker. She's going to provide us with some glimpses into hyperbolic geometry. The floor is yours, Caroline.
Well, thank you very much, Martin, for that introduction. It's very kind of you. I have to say I'm, first of all, extremely honored to be here. It is so nice to be in front of a live audience again. I've got a bit tired of talking into my laptop, but I would also like very much to say hello to all the people out there who we can't see, but who are connected by the wonders of technology. And thank you to the Academy for making all the rather complicated arrangements that have allowed me to come. So I particularly was honored to be asked to give this lecture when I looked at the list of past speakers. You have had some extremely eminent people, some of the world's leading mathematicians. I don't think I'm in that class, but anyway, I'm very happy to be here. So before I actually start my talk proper, switch it on. Right, I very recently was looking in a book I have about the history of 19th century mathematics, looking to answer a completely different question, and I noticed there was a section, a whole section devoted to Hamilton, with this rather nice picture and this quotation, which I thought really shows what esteem he is still held in. Hamilton was a remarkable scientist who invariably obtained deep and fundamental results in the areas of mathematics in which he works. He was one of the best mathematicians of the 19th century. So this was written in 1978 by a group of Russian mathematicians, some of them very distinguished. So this is the kind of level of esteem in which Hamilton is still held. Anyway, tonight, I want to try and give you a few glimpses into the subject which has mainly occupied me for many years. So just to give you an idea, first a little bit about what hyperbolic geometry is, where it comes from, how you work with it. Then I'll start talking about 2 dimensions and, now what? That's right, sorry, okay. Can I go back? Yes. I'll come back to, so I shouldn't touch that. 2-dimensional hyperbolic geometry and the connection with the study of surfaces. Then we will move to the study of 3 dimensions and some wonderful discoveries that were made in the 1970s, 80s, and 90s. And then a little bit about my particular interest, the things I've been doing involving some very beautiful fractal pictures and how that ties in with 3-dimensional hyperbolic geometry. And don't worry, I want to give you some glimpses. I'm going to try largely to avoid formulas and just give you ideas and pictures. There will be one moment when a particular formula will come in I want to highlight, but in general, I hope you can just enjoy the pictures and the ideas and not get too hung up about the exact mathematical formalism. So, what is hyperbolic geometry? Well, it was discovered just about exactly 200 years ago, and the discovery really was one of those great 19th century revolutions that changed people's thinking about the nature of space. So I'll say a bit more about that in a second, but let me say that the way in which the discovery came about, there is something called Euclid's parallel postulate, which no doubt many people have studied. So we know that if we have a straight line and a point not in the line, then there is exactly one line through the point which never meets the straight line, and that's called a parallel line. Well, ever since Euclid, mathematicians really didn't like this very much, because how do we know there's only one such line? How do we know there is such a line? Because in order to really check it, you'd have to go infinitely far, extend the line infinitely. And that's something you can't do in reality. So it's something we have to sort of believe about space, but we're not quite sure. So for getting on for 2,000 years, many people were struggling with this, trying to find a way to deduce this from other more basic, simple axioms. And just about 200 years ago, 3 mathematicians, but all independently, had the idea that maybe the reason we can't do this is actually because it isn't true. Maybe there could be geometry in which you could have several lines through P not meeting L. So these were Gauss, Bolyai, and Lobachevsky. And they all had the courage to go off and investigate the consequences of this idea. Could this happen? Could they find a contradiction? And no, they couldn't. And they deduced all sorts of surprising things. One of them was that the angles in a triangle in this new geometry would no longer add up to 180. They would add up to something less than 180. And in fact, there's a beautiful formula that relates the area of a triangle to the sum of the angles. If you know there's a formula in spherical geometry, there's an analogous formula. So they found a whole, Bolyai wrote to his father, who was also a mathematician, I've created a whole new world out of nothing. It was a wonderful discovery. Now, I don't want to get into the detail of that. Let me give you a slightly later view on it, to perhaps easier to visualize. So we learned that actually the way to think about hyperbolic geometry, it's geometry on a certain surface. A surface that's everywhere shaped like a saddle or a Pringle, as opposed to shaped like a sphere. So here is a kind of mathematical Pringle. There's a saddle here. And as you can see, there are 2 lines drawn on there which look as if they probably never meet. And you can also notice that the triangle drawn there looks a bit like the sides are slightly incurving, which means the angles are a bit less than you think. But this geometry is not just one point where the surface is like this, it's everywhere. And everywhere it's exactly the same degree of saddle shapeness. So there's another way that's a bit more formal to say what this is. If you draw a little circle of a small radius at a point on the surface, you can work out its area, and you can compare it to the area of a circle that you would draw in Euclidean geometry. And you find, if you do that on a sphere, the circle, the area is a little bit smaller than a Euclidean circle. But if you do it on this surface, it's a little bit larger. And out of that, you can make a precise definition of curvature. So here is a piece of surface which is everywhere got this saddle shape. It's actually a famous theorem that you can't embed a surface like that totally in ordinary Euclidean 3D space. You'll come to some singular point where it gets too crinkled up. So a more simple way to think about it is, you can think about it, we're trying to do geometry on a surface a bit like this crinkled up leaf of kale. Right, so, well, that's all well and good. How do we actually do it? So what we do is, just as if you're trying to study geometry on the sphere, the best thing to do is project it onto the plane. You take a map projection, like in an atlas or a map, and there are various ways to do that. Well, so there are various ways to do this with hyperbolic geometry, and this was one of the reasons why people concluded in the end that this was a perfectly legitimate, logically consistent system. So we're going to project the whole picture into the inside of a circle, mathematically a disk, but we won't include the boundary, but our whole universe is going to be projected inside, and we're going to set up a way of measuring distance, a metric, in such a way that the shortest paths in this geometry, this metric, are going to look like to us circular arcs of circles which hit the boundary circle at right angles. So here's a picture with some straight lines, but they get distorted in this picture, although the angles aren't distorted. So, right, now here's a picture. You may recognize this looks a bit like some Escher pictures. There are a few Escher pictures like this. So this is one done by a wonderful modern graphics artist. Oh, I can see I've put Joe Lays. He's Joss Lays. He has a wonderful website. It's quite expensive to get copyright permission to reproduce an Escher picture, so you're better off making your own. So, thing to notice, two things. These shapes, they look different to our eyes, but they're actually all the brown shell-like flowers are actually the same size and shape in this new geometry, but they seem to get smaller and smaller as we go to the edge of the disk. But the angles between the petals don't change. So angles are okay, but everything else is distorted. And as you go round to the boundary of the disk, you actually get more and more, exponentially more things. So the next picture, no, not quite the next one. Here is another picture, another tessellation picture with some triangles. So tessellation means a tiling by triangles, and we can see on this quite clearly some of the features of geometry. So if you look at that green, the sort of blue-green star, you can trace out, there are quite a lot of lines in the picture that go through the star, like this one, which never hit, for example, this red line. So actually, there's not just one line through here, there's several lines. There's a line here that never hits the green one, there's another line here that never hits the green one, and so on. So you can see this lack of the parallel postulates, and you can also work out pretty easily the sum of the angles in a triangle. All these triangles are the same. So in fact, 14 of them meet at the points where there are lots of triangles. So the angle in one of those is pi over 7, and so the sum of angles in a triangle is slightly less than pi, in contrast to this Euclidean picture in which you can easily see that the angles add up exactly to pi. So this picture kind of illustrates some of the features. Now the next, is this going to, yeah, this is going to work for me. This nice little movie illustrates more concretely. So we're flying over hyperbolic space, and we are seeing that the triangles are all in fact the same, right? We're sort of moving over our map projection. And you can also see what's happening, that as we go on, the boundary that was a circle seems to straighten out, and it gives the idea of another way of modeling hyperbolic space that I want to use, called the upper half plane model. So, well, two things. We're going to see a bit more about the upper half plane model, but this visual horizon, it just recedes into the distance forever. And so we never actually get to the boundary. It's called the boundary at infinity, and that's going to play a role in what I have to say later. So, upper half plane model then, different way of looking at things. It's like a different map projection. We're going to take all the part of the ordinary Euclidean plane that's above the x-axis, and now the straight lines are going to be either vertical lines or semicircles with their centers on the real axis. So that's a nice, simple picture to have. And here is another Joss Lay's picture where he's done the same tessellation, but he's done it in a different projection. And a formula, you don't need to worry too much, but there's a formula to tell you how to measure distance. And the thing to notice, it's almost the same as measuring Euclidean distance, but when the y value gets very small, that means you're down near the x-axis, then the factor 1 over y squared gets huge, so distances, it makes things look very small, but actually they're all the same size. So, yeah, once again, the boundary at infinity, and hang on to that because we're going to come back to that again when we get to 3D. So, let's go on now to look at tessellations and surfaces, and I'm going to first start with a bit of Euclidean geometry connected to surfaces, and then see how hyperbolic fits in. So here's a very simple picture of a square tiling of Euclidean plane, and all the squares are the same, all the tiles are identical. We can move any one and plonk it on top of any other. And if we take one of the basic shapes, then, well, we have two basic motions. We can translate it left to right, or we can translate it sort of vertically up in the picture. And as we go vertically up, we would end up gluing the bottom side to the top side and making ourselves a cylinder. And then as we go from right to left, we glue up the two ends of the cylinder and we make a donut. So that's a simple construction. But you could do this, what we say topologically, without measuring distance, but the important fact for what I want to say is we've kept the geometry intact. So if you were a fly walking around on this surface, you really wouldn't know if you looked at a little patch around you, are you in the whole extent of Euclidean space, or are you on this surface? So just in little patches, even when you're near the seams where you've glued up, it doesn't matter. Even at the corner where all the seams come together, the total angles, you've got 4 angles of right angles, it adds up to 360, so it glues together and matches up perfectly. So we say this torus has a Euclidean structure. Right, so now let's look a little bit more how we actually made this thing. So this is still very simple-minded Euclidean geometry, and I just need a little bit of notation. So the idea of doing a translation, so the red man moves backwards, implemented by t, it just translates him back. If I want to move him forwards again, I've got to undo the effect of t, and that's denoted by t minus 1. That's just a standard mathematical notation called the inverse of t. Right, so how did we make a tessellation? Well, we start with 2 parallel lines, and we move one onto the next one, certain distance, by a translation A. So we make 2 parallel lines, and then we do again. We now take a perpendicular line and translate that one, and we've made a square, and we keep repeating the same moves. So we repeat the moves and their inverses that undo them in any old order. So we get from L, we went to A of L, we do it twice, we get to A squared of L, we went back, we get to A inverse of L, we do it with the B's, and you can see if I keep doing that, I'm going to build up my tessellation, and that's related to this torus. So that's not very hard to understand. Let's see how that works in hyperbolic space. So another bit of terminology that's useful to have, if we look at the collection of all these things, A's and B's and A inverses and B inverses, all repeated, that's called a group. Okay, so let's do the same thing in hyperbolic plane. So we start with 2 parallel lines, which just means 2 lines which don't meet in this disk model of the hyperbolic plane. and we take a translation A that takes one to the other one, just the same idea. And now I'm going to take another pair with a B, but I'm going to make a slight difference with Euclidean case. In the Euclidean case, I made the B lines meet the A lines at right angles. Now I've made them actually meet at a 0 angle, and this picture isn't very good, but really these two lines, hyperbolic lines, go out all the way to the infinite boundary, and they never meet inside hyperbolic space, but they'd meet at some ideal point on the boundary. And the reason I've done that is because well, all right. We'll come to the reason in a moment, but there's a critical difference between this Euclidean, this hyperbolic one. In the Euclidean one, if we did, it didn't matter, if we did A then B or B then A, we'd come to the same thing. So here's a Euclidean picture again. To get from the blue square to the yellow square, we can either do A followed by B, or we can do B followed by A. In the hyperbolic picture, what happens is, if we do A, we take this four-sided thing, and it turns into a four-sided thing here, which looks different to our eyes, but really it's the same, congruent. And if we do B, this one here moves up to this one here. But now if we take this one and we apply B to this one, we land here. Whereas if we take this one and apply A to it, we land here. So there's a difference between doing AB and BA. And that means when you start doing them all in any order over and over again, you get vastly more possibilities. The things, if you're a mathematician, doesn't commute, you get vastly more possibilities, and that's really why we get this exponential growth in the number of tiles. So how are we going to keep track of this? Here is a nice picture, which is arranging all the possibilities. We're using a kind of shorthand here, so little b is short for capital B inverse. It's just easier to keep writing. So this diagram is showing all the possibilities of what can happen. Every time you've got to a certain tile, you can do various further things to keep going further out in this picture. You can do 3 more different things, in fact, and they're all arranged in this tree-like thing. This is called a Cayley Graph, and I learned recently that the mathematician Cayley was a generation younger than Hamilton. As a young man, he actually traveled to Dublin to study with Hamilton, and I believe he was the first person who wrote the paper on Quaternions after Hamilton, which of course pleased Hamilton greatly. So, mathematics is all connected. So here is another version of the same picture. So now we've gone back to our tiling, but instead of being a 19th century picture, this is a late 20th century picture. We've got the tiling, and this character is called Dr. Stickler, and perhaps this is a good moment to show this book I wrote with David Mumford and David Wright here, which I shall leave behind with the Academy, introduces this character and uses him to illustrate a large number of beautiful constructions you can make. We wrote the whole book without actually explaining it was all connected with hyperbolic geometry, and we wrote it hoping that people who were in their final years of school or beginning undergraduates would be able to appreciate it. Anyway, it's not quite the talk today, but a number of the pictures I'm showing come out of our book. So, and from this tree, you can easily work out how many tiles you have after n steps, and you can see it grows exponentially. Not in the vague sense of exponential that politicians use nowadays, but the real, true sense of exponential. Right. So, we have tiles, tiling, a construction. Now we're going to make a surface. So what are we going to do? We are going to glue up the opposite sides of this tile, just as we did before. But now, instead of 4 right angles coming together to make a 360-degree angle, these 4 zero angles come together, and they don't actually meet at a point because that point is missing. So the point is off at infinity. So the red star is supposed to indicate that it's infinitely far. This missing point has been stretched far away. So if you are a fly living on this structure here, you will never actually reach the puncture. So there's a missing point, but you're never going to get there. So you don't know it's there. So as far as you're concerned, this surface also is like a little piece of, it's everywhere like a piece of a hyperbolic surface. So we've made what's called a hyperbolic structure on this surface. Now, in fact, I've done a very simple example, but this turns out to be a much more general thing. So in this picture, this is just a topological picture with no measurements. You may have seen that if you take an octagon, you can glue opposite sides together, and if you twist your mind around enough, you can convince yourself you come out with a torus with 2 holes, a 2-hole donut. Now, supposing we wanted to put a geometry on that surface. So far, we've done something sort of without measuring, without geometry. If we did it, we'd have to make sure that the angle where all these vertices come together added up to 360. And we've got 8 things coming together, so if we wanted to make a regular octagon, we'd have to make the angle 45 degrees, but Euclidean geometry is very rigid. The angle in an octagon you can calculate as 135 degrees, it's hopeless. But in hyperbolic geometry, we can concoct triangles with any angles we want. So here we are, we can make a tessellation, and we've stuck together a number of triangles in which the angles are correctly set up so that when we glue all these corners together, we get 360 degrees. So we have produced a hyperbolic structure on this surface. So that was a very important observation about 100 years ago now. And what's actually remarkable is that any surface that's more complicated than a torus or a sphere can be manufactured in this way, out of a piece of hyperbolic plane. So we say that all these surfaces have hyperbolic structures, and this became very important for understanding dynamics and understanding curves on surfaces and so on. I spent a lot of my life studying the trajectory of geodesics across this picture, how they cut the different shapes in the tessellation almost like randomly, statistically. Very interesting questions. So every surface, almost every surface has a hyperbolic structure, except a very few very easy ones that we can handle anyway. Right. So that's 2D, lightning fast introduction. What about 3D? Well, you can easily imagine, I told you how to make 2D hyperbolic space. There's a 3D, in fact, an n-dimensional version. And if I took some sort of shape, regular shape, or maybe not regular shape in 3D hyperbolic space, I could glue up opposite faces. And if I was clever, I could make it so the angles, when a number of different copies of this dodecahedron or whatever it was came together around an edge, would add up to 360 going around the edge. There's a wonderful theorem that says if it works around the edges, it'll work around the vertices. So we can make shapes, and they are the 3D analog of surfaces, for which there isn't a word in the English language, but mathematicians call them manifolds. So you can make manifolds. And so you can make manifolds, and if you're clever, you can manufacture one which has a hyperbolic structure. Here is Another picture, so once you've got a basic crystal shape, you've got your gluing pattern, it goes with a tessellation. It is not easy to draw a 3D tessellation by any means, but Jos Leys has drawn various beautiful pictures which you can find on his website, of which this is an example. So this is what a chunk of a tessellation in 3D looks like. Well, up until around the mid-1970s, these things were sort of curiosities. There were examples, and they were very nice examples connected with number theory, some of them, but they were sort of a bit obscure curiosities. And then the American mathematician William Thurston came along and completely changed the worldview of this. So he had the insight to see that these were not just isolated examples. In fact, he showed that enormous numbers, in fact, most, in some sense, three-dimensional space forms actually could be given a hyperbolic structure, and we've learned what a hyperbolic structure is. So just as with surfaces, hyperbolic geometry came in, so in 3D. So here's an example. So you draw a knot, and by a knot, a mathematician means you sort of tie a thing in a piece of string and you join up the two ends. And you imagine taking that thing in 3 dimensions and drilling out a little hole in space along the course of where this knot was. And now you've made a 3-dimensional object. It goes off to infinity, but there's a missing, not just a point, there's a missing little tunnel. Okay, so could you make a hyperbolic structure on that? And to do it, you'd have to make it so that the tunnel that was missing would be infinitely far away. Otherwise, you'd hit the tunnel and you'd come to a nasty end. You don't want that. You want the tunnel to be infinitely far away, and you want it to be nice, consistent geometry everywhere. And Thurston showed that with very few exceptions, any complement of a knot, so we can list the knots that this doesn't apply to, they're quite easy to understand. Any other one can be made into a hyperbolic structure. That means there's a tessellation, there are some transformations that glue up sides of some basic crystal, and that's led rise to a beautiful, enormous discoveries and theories. So here is a picture. So one of my colleagues saw Schleimer at Warwick and Henry Siegermann. He's not at Warwick, but a mathematician. He's sort of a mathematical artist. They have started manufacturing beautiful 3D printed geometrical shapes. If you search for Henry Siegermann's online, he's written a book and he's also got a website. You can actually order one of these things with all sorts of beautiful shapes. And this particular one shows this space is kind of twisted up there into this particular knot, and you have to imagine that inside that knot, space recedes to the infinite distance, and right in the core of it, as it were, there's a hole, the missing tube. So that's what Thurston was talking about. In fact, this knot was one of the first ones that he really explained how to study. So Thurston introduced, in the course of what he did, he introduced loads of wonderful, new, very powerful ideas. Something was set up called the Geometry Center in Minneapolis. They had a very high-powered computer. This was in the 1980s, very high-powered for that time. And he also got together lots of students, and he taught these sort of classes where people, you can see they're studying, I think, the curvature of a piece of orange peel. He had a great, very visual, tactile imagination, but also an absolutely brilliant mathematician. He attracted a lot of brilliant students. So this was a picture created at the Geometry Center, one of the first pictures of what the inside of hyperbolic space looks like. So the greatest result of Thurston's was not only did he say lots of manifolds like these knot complements are hyperbolic, but he went much further. It was known that you could cut up a manifold into pieces, but you didn't quite know what was inside the pieces. And he showed, basically, that each of these different types of pieces had a particular geometry, and most of the pieces were hyperbolic geometry. Some of the pieces were, in fact, somewhat simpler geometries, and it's very curious that the only manifolds he couldn't handle was the most simple thing. Your piece is a three-dimensional sphere. That he couldn't handle. That was the content of the famous Poincaré conjecture that I'm sure some people have heard about, and that was what was proved by Perlman not very long afterwards. So now we have a complete picture of how you can make geometry on all these three-dimensional space forms, which of course has many ramifications. Now, I'm not going to even attempt to explain that anymore, but I want to talk a little bit about, go back to be a bit simpler, how do we actually work at all in three-dimensional hyperbolic space? So we're going to go, we had the upper half space in 2D, now we've got we had the upper half plane, now we're going to go to the upper half space. So we're going to take a base plane, which we can think of as an XY plane, and then we'll have a vertical direction, which is we'll call it the t-axis, and everything above this base, but not including the base itself, will be in this 3D projection model of hyperbolic 3D space, and it doesn't take much imagination to think that lines will be semicircles again, planes will be hemispheres with their centers on the base plane, or possibly vertical planes. So we have a very similar model, and there we go. So we don't include the boundary, but everyone else is there. Everything behaves more or less in the same way. And the thing at the bottom we're going to call the boundary at infinity, because wherever I stand here, it's going to take infinitely long to get down to a point on the boundary. But now the boundary is kind of nice. It's a two-dimensional plane, XY plane, but it turns out that it's very useful to introduce complex numbers at this point. So we're going to think of the bottom as being complex numbers, z equals x plus iy, and to be strictly honest, we have to add in one more point that's sort of off at infinity, sort of round up there. So anyway, don't get too hung up on that, but we have to introduce that extra point. And then what are we going to do? Well, let's have some formulae. So I said I was going to have one lot of formulae. So I haven't told you yet, you couldn't yet really do what I'm telling you because I haven't told you any formulae, right? Well, start in 2D. So here is a picture, and now we're in the upper half plane, but I'm still going to write things down using complex numbers. I hope that's not too confusing. So we've got z equals x plus iy. So the point with coordinates x, y, we're going to introduce the square root of minus 1i, and it's just easier to manipulate, neater to write down. So there's a very nice formula that tells you what all the rigid motions that pick up the plane and move one tile to another look like. They take this particular form, so you pick any four real numbers, a, b, c, and d, which have the property that AD minus BC is 1, sort of their determinant is 1. And then you write down this formula in complex numbers. You say Z should be sent to AZ plus B over CZ plus D. That's called a Mobius map or a linear fractional transformation, and these have been very much studied. Some people may have come across these in a course, a mathematics course somewhere, so they've got a very nice, relatively simple form, and they turn out to represent exactly the motions in this geometry. So now we want to do 3D, okay? So we're going to have x, y, and t. So the thing we aren't allowed to do is have t equals naught. And, right, the reason I wanted the formula is because it turns out what does the trick is exactly Hamilton's quaternions. Okay, so we haven't gone into 4D, we're only in 3D, but never mind, we can represent a point. So remember, I'm sure everybody here knows about quaternions. Instead of having just the square root of -1, we have another thing j and another thing k, both of which are also squared to -1. And the product of all three of these things is also -1. So something like I times j is k or minus k. Anyway, so there are rules for manipulating quaternions. And I'm going to write down my point in this 3D space using just the I and the j. So I can write it with the complex number z and a j times t. So what would you guess that the formula for a rigid motion is? Here we go. So instead of taking 4 real numbers, a, b, c, d, we take any 4 complex numbers with ad minus bc is 1. And here is the formula for the most general rigid motion of hyperbolic space, like this, right? So z plus jt at some point here gets transformed, and you can see it very similar to this. We've got these extra j's, and we have to be careful because quaternions don't commute. So now it matters which order we do multiplication. So we have to put, instead of putting this over this, we write it down so it's on the right so we know which way we're doing it. So the formula doesn't involve any k's, but the minute you start trying to calculate with this and you stick in some point and you want to see where it moves to, you find you have to put the k's in as well. So that's right. So that's what the formula is. There are other ways of doing it, but this is a particular way. This is all getting a bit hairy. And we don't really like doing things that are so complicated like this. It turns out that actually, rather than doing that, we can, now having said this plane at the bottom is away to infinity, it is, but nevertheless we can study what goes on there, and it tells us a great deal about what's happening inside. So that's going to be the trick. So rather than trying to draw a tessellation in 3D, we are going to stick ourselves onto the boundary at infinity and work there. Okay, and so what's the formula? We just had the formula with quaternions here. And so how do we tell what's happening at infinity? Well, we just drop the t. We set t equals 0, and that means we're on the base. So we set t equals 0 in that formula, and you get this nice formula, which is exactly the same as the formula for 2D rigid motions, except that the A, B, C, and D can now be complex numbers. And maps like this are called Mobius maps. Their properties are, they're a very beautiful class of maps. Their properties are all very well understood. So a Mobius map, we've gone off to infinity. We've sort of lost the geometry. So they are not any more rigid motions of anything. They distort distances, but they do have two very important features. They send circles to circles, but maybe change the size, and they keep angles the same. So here is a picture of the effects of just, you write down some, more or less any A, B, C, D, and you draw a picture of Dr. Stickler, and then you keep hitting him with one of these transformations over and over again, and see what happens to him, poor man, and he gets sort of pushed around, he contracts, he expands, and you can see he keeps walking and he sort of lands in a black hole here, and if he goes backwards, he lands in another black hole here. But all of these pictures, he's all distorted, but his head stays more or less round, and the angles of his ankles stay the same. So there's some coherence to this, and you can see he moves in a spiral. So you can say, well, let's take a group, a collection of these 3D rigid motions. Let's drop the J coordinate, and let's just look what these transformations do down on the plane. And let's explore that and see what we get. And that's really what the content of this book, Indra's Pearls, is about. You get beautiful pictures, and you don't even need to mention the fact that what you're really doing is this footprint of 3D hyperbolic geometry in the plane. You can just work with complex numbers. So let me show you just a little bit. Here, these are some pictures from the book. So let's start with 4 tangent circles. So now we're in the complex plane. Take 4 tangent circles, take one Mobius map that takes this circle to this circle, and actually it's quite important for what I'm going to say. It takes all the stuff that's outside this disk here, inside this disk here. And the stuff that's inside here gets expanded out around this part here. So if you do that and you think about it, what's outside this circle? Well, there are 3 red circles. And they get pushed into these, there's a little one here, 3 yellow circles inside here. And if I push this circle to the outside of this one, these 3 things get pushed into here, and so on and so forth. So the labels, you have to put a bit of thought in, but you can find a way of labeling this so you keep track of all these circles, and then you keep doing the same thing over and over again. And this is explained in great depth in our book in a way that I hope is sort of comprehensible. So you keep on doing it over and over again. What happens? Well, if you did it once to Dr. Stickler, he had 2 black holes. He came out of one and he landed in another. If you do it with all these simultaneous transformations together, then all the black holes sort of accumulate in this beautiful glowing yellow thing. So all these images of all these disks accumulate like this. And once again, what we're really doing is we're following this recipe of the word tree. We're taking all these transformations. We start with 2 Mobius maps, and then we repeat them in any order following this, and we systematically compute where all these original circles go to, and we land up with this picture. And this thing is called the limit set. And what's it a limit set of? Well, it's a limit set of the group that I got by starting with 2 transformations and just repeating them in any order. So we can make a picture of a limit set. Well, let's see a little bit what's going on in 3D. So if we put this back above the plane, we put it back into 3D, these disks would be the base of hemispheres that were planes in 3D. So what have I really done? I have taken 4 hemispheres, and there was a region, they sort of take out chunks of this space, and there's a bit left. And if you think about it carefully, you can see there's a sort of chimney that comes up, starting from this patch here, and coming up here, and going around the outside and landing here. It's easier to see if you imagine drawing it on a sphere. And it's just like matching 2 pairs of parallel lines in H2. And so what I've done now is I've really taken 2 planes, 2 parallel non-meeting planes, and I've pushed one over to the other one, and it glues up, all right? And then another pair and glue them up. In 2D, I got a torus with a missing point. What do I get now? I get a chimney, and I'm going to glue up its opposite sides, but each cross-section was a 4-sided thing, which was a torus with a puncture. So I'm going to create myself a thing which is an infinitely long thing, and if I take a section of it anywhere, I get a torus with a puncture. And that's a 3D manifold, and there is a bit here off at infinity, looks like a straight line, but that's how to make a very simple 3D hyperbolic manifold. Now that's probably a bit hard to get your head around, so let me show you what happens in Euclidean geometry. It's easier to see. So here we've got a chimney that we've made. We took two parallel planes, we glued one to the other, and then we took another pair and moved that one to that one, and we made our chimney, and we glue out the sides, and this time we make a sort of infinite stretch, and each level is a torus. So I've done the same thing, but I've done it in 3D, and I've cheated a bit in the hyperbolic case, because really the top torus and the bottom torus might be quite different as structures on the tori go. So actually the interior geometry of this is all very, very complicated. So they are tori, but they can be long, thin ones or short, fat ones or squished around. And one of the great things Thurston and his students did was really discover, elucidate all the internal geometry of these things, which is a very beautiful, even in this simple example, a very beautiful piece of mathematics. But let's continue. Limit sets are really interesting in their own right. If you didn't know anything about this 3D, you get beautiful pictures. So I told you how to make the pictures. David Mumford and David Wright, in the late 1980s, when computer graphics was really in its infancy, started exploring these pictures. They'd been known about theoretically since the late 19th century, but how would you draw one? But they were able to draw them, and they came out with really astonishingly beautiful pictures. Here are just a couple of examples. And you can see lots of spirals which come from this basic iteration of a single map. And as you change the A, B, C, and D, as you move them around a bit, the shapes change in most intricate, fascinating ways. So I'm not going to really have time to go into how that works, but I want to say just a little bit about how I got interested in this. So I started seeing some of these pictures sometime in the late 1980s that Thurston and his Mumford were producing. And, well, they're just beautiful pictures. I really loved them. And I looked and I said, but what are all these, why are there all these white circles? And even more, these kind of gray things, which are like sort of circles, but then there's sort of another bit that overlaps and overlaps. And what's all that? What's it all about? And nobody could really explain to me for quite some time. Finally, another Fields medalist, Kurt McMullen, gave a hint. But anyway, it turns out that the key to understand this picture, although it's entirely a thing you make in complex numbers, 2D, to really get a grip on what's going on, you need to go into 3D hyperbolic geometry and use one of Thurston's ideas. So let me very quickly, just to give you an idea of the sort of ideas he came out with. Here is a picture. So what's this? We've taken a flat piece of hyperbolic paper in 3 space, and we started bending it, bending it, bending it. And these sort of domes are like hyperbolic planes. So I didn't bring it with me, but if I had a piece of paper, you just take a piece of paper and you bend along a parallel line and another line and another line and see what you get. And the points where these dome things come down to the boundary turn out to be exactly the same as a limit set associated to this configuration. So bending, let's do bending in 2D. If you take a Euclidean line and you go along a bit and you bend it and you go along a bit more and you bend it, very soon you're going to come back. You'll either join up with yourself or you'll start going round and around, crisscrossing. But in hyperbolic space, there's much more space. So you go along for a distance and you bend, and as long as you go along a reasonable distance, depending on how much you want to bend, and then you go along a bit more, you never come back and hit yourself. You keep going and going and going. This is a very important principle, and in fact, it's a theorem that you can find a straight line that sort of tracks this thing, and that's a crucial principle in chaotic dynamics, that you can do this. So you can bend, 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 and you don't hit yourself, you go off forever. So what Thurston was doing was he was starting with a hyperbolic surface and choosing a family of lines on it, and then taking the tessellation that went with that and bending and bending and bending. And so again, we get this same picture. So this sort of, we had a tessellation that was a surface, and we bent, bent, bent. We didn't collide with ourselves, but we come down to the boundary along a crinkled up limit set. And this picture on the right shows you really the opposite. You start with a limit set, and you can reconstruct this bent surface. And the reason there are all these circles drawn inside here is that to find these dome-shaped things, you start drawing circles in here, and you expand them out till they're as big as they can possibly get, just hitting the limit set but not going outside it. And when you find one of them, you drew a dome, and then you keep doing that all the way along, and that's how you get back. You sort of desingularize this very complicated thing and get to this thing. So Thurston, and particularly his student, another very brilliant mathematician, Yair Minsky, made great inroads in mathematics by using this idea. If it's a more complicated surface, you can bend not just that way, but you can bend sometimes that way and sometimes that way. It gets more complicated. So what have we done? We started with hyperbolic 3-space. We had a complicated formula that was a bit hard to handle, so we just went down to the boundary at infinity. We did a lot of exploring, and then we found a way to go back from down below to up above. So, yeah, so we went from a rigid motion in 3D to a Mobius transformation in 2D. We had groups coming in, more than one at a time, and then we went from three-dimensional space forms to 3D tessellations to limit sets, which are fractals. I don't really have time to explain about a fractal, but they're very, very complicated shapes that we get in 3D. And Thurston and his students made this construction into a really crucial tool in understanding the internal goings-on in one of these hyperbolic three-dimensional things. So one of the things that I've spent quite a lot of time on, my original question about what's going on with these limit set pictures, and as you change the parameters of the transformation, why do the pictures change? Why do they sometimes collapse? I was able to understand that in a very concrete way and make calculations using these ideas in 3D, a problem which seemed really, I spent several years in 2D, and it was hopeless, but in 3D, you've desingularized, you use Thurston's wonderful ideas, and you can really do some things. So I'm not going to try and send any more hard mathematics, but you might be sitting there thinking still, well, you know, this is all pure maths, what's it good for? So let me just tell you a few things. So first of all, the discovery 200 years ago. It was a great liberation away from having to think that the universe is strictly according to the God-given rules of Euclidean geometry. It's not. It might not be. It might be, it might not be. It was a liberation which was argued about for at least half a century, but eventually people got convinced, or at least mathematicians were. It turned out that hyperbolic geometry allowed the development of the idea that space itself might be curved. We saw about a curved surface. And that led in the mid-19th century to the development of differential geometry, Riemannian geometry, that allowed one to handle the sort of calculus of how you would deal with a curved space. And it turned out that all that mathematics that was developed was sitting there and was the right mathematics for Einstein, first of all for his special relativity, which uses the transformations of 3D hyperbolic geometry, and then later on for general relativity, there was sort of a mathematical formalism for dealing with curved space. So that was very important. Then in the 1920s and 30s, studying surfaces, particles sliding on hyperbolic surfaces turned out to have a motion that was chaotic in the sense it's deterministic, but it goes round and round in such a complicated way it looks random. And they were among the very first examples of chaotic, what we now call chaotic dynamics. So those were very important examples that later developed into a whole big theory of what mathematicians now do in dynamics. Thurston showed us how to use hyperbolic geometry in 3D. I would say there is still a lot of things remaining to be done in the applications of that. There's a bit done, but there's surely a whole lot more out there that hasn't been done yet. We know how they work now. We've got the tools. They're not easy. We've got computational tools, but there's surely a lot to do with them. We've seen some beautiful patterns, and a certain amount of artwork has been inspired by some of these beautiful patterns I've been showing you. So that's a kind of 3D things and 2D things and so on. And finally, something I've got a bit interested in recently, there are a lot of recent applications of hyperbolic geometry in all sorts of different areas of science. So questions about plant growth. I showed you a crinkled up leaf. Well, when a leaf grows, it adds cells around the edges, and it crinkles. Well, why? How does it decide to do that without knowing a global picture? It just knows a local picture. You can use methods akin to hyperbolic geometry to try to model that. Hyperbolic geometry has inspired architecture, and then particularly, it turns out that hyperbolic geometry is very good for representing sort of hierarchical data. We saw this word tree, which would be very hard to fit into ordinary Euclidean space, but it fits nicely into hyperbolic space. So there's quite a lot of work out there now in data science and visualization, which is understanding that sort of, in some sense, the best geometry to use to do it is hyperbolic geometry. So I think I've completely lost track of time, but I think I'll stop there. Thank you very much.
Thank you very much, Caroline, for this fascinating talk, which spans a whole world of different areas of mathematics and very modern applications to data science, which is, very much in flow. Do we have any questions from the audience here already? Maybe somebody wants to ask a question, and then you just raise your hand and the microphone comes directly to you. Let me see if we have a question already here. Yeah, please. If you bring the microphone to the...
Thank you. It's a very nice talk. I just have a quick question. Hamilton is definitely a very great mathematician, but also he's very great physicist as well. So my question is a little related to the physics. So just a few days ago, this year's Nobel Prize in Physics is awarded to the work on complex system. And the final part about the chaotic motion, which is definitely quite have many applications in similar field. So my question is, for example, in nowadays there are some few complex international problems we need to solve. For example, the climate change. So my question is about the geometry today. You talk. Do you have some idea or did you work on this field to use the geometry to solve the complex system problem?
I'm sorry, can we ask you to take your mask off?
Yeah,
it's really
it's
hard.
very hard to
I think
understand.
I'm sure it's hard for you. Take your mask off.
Oh, really?
Just ask
Yes,
me that
please.
question,
Oh,
part
okay,
of the question.
okay,
again. Thank you. Yeah,
okay,
thank you.
yeah.
Yeah.
Okay, I just briefly to
Yeah.
repeat again.
Yeah.
Yeah. So this year's Nobel Prize in Physics
Yeah.
is awarded to the work which is about the complex system. Half is to the climate change. The other half is about the quantum physics, about the spin glass complex system as well. So my question is, especially the final part, the chaotic motion, or the most part about the hyperbolic geometry. So did you work on to apply this mathematics to solve some complex system, or so this is for the past, and for the future, do you have some idea or comment to say how to apply this to solve some those big international problems?
I think most of the people that I know working in this subject are not directly focused on solving any particular real-world problem. It's more been an adventure in ideas, and it's turned out that the ideas have had quite profound implications for the way people think. Okay, so it's not that somebody sat down and said, how do I design a chaotic system? That's not quite true, actually. People were trying to do that, but it's more that someone was playing around with hyperbolic geometry and a tessellation, and they realized they were creating a system which had very strange and unusual properties, did not behave like a sort of standard periodic motion. And as I said at the beginning, this idea that space could be curved, so then people sat down and said, right, how do we develop the technology to work with it? And later on, it turned out that this was really important. I mean, it's important for Einstein, it's also important for all kind of modern kinds of modeling, right? You constantly got a complicated shaped surface or computer graphics. You have to use Riemannian geometry. You know, that's the way to do it. So, but if we were still stuck with thinking we had to be in Euclidean space, no way. So these most recent things are based on the idea that tree-like structures are there. They don't have to be quite trees, and they don't have to be perfect, you know, but they're kind of there a lot in the world, and it's a good way of describing things. And different kinds of scientists are now learning about it and saying, right, that's just the thing I need to represent my data in some way. So that's kind of the way it's gone, usually. I don't know if that's an answer. Yeah, okay, thank you.
Yeah, I think actually, if I may add something, that this is a typical way mathematics works. It's largely, or to a large extent, driven by curiosity. And I think that's probably what drove Gauss, for example. I mean, there was this thousands of years old question about the fifth postulate of Euclid, and people were intrigued that they could prove it from the four other postulates. And they just kept going. And of course, they didn't think about data analytics or about general relativity. But they were driven by curiosity, and they found something new. And then, because it was already available, for example, Einstein could work with it and other people. And that's how mathematics works, it seems, over the centuries, over the millennia.
It's not completely. It does go the other way. I mean, problems come up in computing. You try to tackle them, and you get the idea of some new mathematical structure. So it is a two-way thing. Problems in physics lead to mathematics. Yeah, but I think this subject has largely been driven by the curiosity angle of it, yeah.
So I have just a question coming in here from David Malone, if I can read it before it disappears here. So he writes, one of the great modern applications of geometry is in video graphics and games, where there is a lot of geometry going on just below the surface. You have given some lovely examples of art based on hyperbolic geometry. Do you know of any computer games that use it? Probably there are some, but one doesn't
There
quite.
probably are some, but I'm not a computer game person, I have to say, and I couldn't tell you one. But if it would be a good project to go and make some, because I'm sure you could. I actually have a couple more slides I didn't have time to show you, and maybe let me,
Yeah.
a couple of little movies, see if I can. Yeah. Okay, so I've said that a limit set is a fractal. I didn't explain what a fractal was. So this is constructing a particular limit set by the algorithm that Mumford and Wright developed. So we have to be a bit, it's going around the boundary of the word tree at some very far distance, plotting the black holes that Dr. Stickler would drop into, more or less. And this is what you get. And in just a minute, when it joins up, right. So now we're zooming in to another place, and then we're going to zoom in, and this is telling you, this is what a fractal is. Exactly what a fractal is. So every time you zoom into a particular piece, the same structure repeats itself deeper and deeper. And it turns out that all limit sets have this property, this wonderful property, unless they're just what mathematicians call round circles, just bog standard circle. So that's one picture. And the other picture that you might want to see if this one works. Yeah. This was made at the Geometry Center. So this is a clip from a movie. This is actually flying around in hyperbolic space, and it was a movie explaining how it is that a complement of a knot could have a hyperbolic structure. And this was just a masterwork of a combination of mathematics and programming, this movie. Doing this stuff. Thurston was there in the background, sort of, no doubt, giving all sorts of ideas, but just imagine the programming that goes into that. And interestingly, I learned recently, Charlie Gunn, who was the programmer who did this, was actually the first person to suggest that if you had hierarchical data structures, maybe it would be good to represent them in hyperbolic geometry. So that's sort of an example of how this very abstract thing that was going on, and here's a guy computing, and he has this idea, let's represent data in a different way, which turns out to be, you know, a hot topic nowadays. So, yeah. Yeah, okay, thank you.
There's just another question that came in from a non-mathematician. Are there any particularly interesting examples or considerations for shapes with non-Euclidean geometry in 4 or more dimensions?
Yes, there are. There were very beautiful, particularly examples that come out of number theory in hyperbolic geometry. But the study of 4-dimensional manifolds is also a wonderful story, but it really has nothing or almost nothing to do with hyperbolic geometry. 3D is somehow special. So, yeah, you can do hyperbolic geometry in any direct dimension. There are, yeah, very nice examples, but there's not this sort of tactile feel about, you know, what this is saying about actual topological shapes in the same way. Yeah.
Another question from the audience, maybe? Yeah, here, I'm here.
Hello, my name is Laurie and I'm a physicist, so apologies if this question just sounds weird.
Speak into the microphone.
Sorry, yes, can you hear me all right?
Yes.
Okay. Very good talk, by the way, thank you so much. I guess my question was, because it's not clear to me whether or not hyperbolic geometry as a formalism is comprehensive in the sense that it almost like includes the possibility for some type of an inception of hyperbolic space. That is to say that if you were like to try to represent hyperbolic space using hyperbolic formalism, there would kind of be like levels of hyperbolicness, or is hyperbolic geometry just comprehensive in that it already compensates for that?
Okay, if I understand, let's see if I can explain. So there are rules entirely analogous to Euclidean geometry. You can do trigonometry, there are precise formulas. There are also general principles that you can use. So yeah, there's a whole formalism and different ways in which you can do it. Does that answer what you're asking or not? I'm not quite sure that's what you're getting at. And let me say, there's also a concept, what I've told you is a very tightly formulated thing. Another brilliant mathematician, Misha Gromov, had this wonderful idea. He managed to abstract the kind of key points of what's really important, what's really going on, and this business about bending a line and you never hit yourself, and the business about exponential growth as you go out. So he formulated a condition in terms of any sort of setup in which the triangles are kind of thin. They don't, the sides kind of bend inwards. And just a very simple rule, and then all sorts of networks and geometries and other things all have these hyperbolic-like properties. So you don't have to be so tight in your formulas anymore. You can say, well, this is going to work because it's called a Gromov hyperbolic space. So it's sort of a loose picture, but it's a tremendously powerful idea. So, and there's now grown up a whole school of what's called coarse geometry, where you kind of let go of the rigid properties, but you kind of try to discern what are the sort of underlying important points about what's going on, and just work with those and see how far you can get. So networks can be like this Gromov thing, and that tells you things about the way paths travel and how many paths there are and so on. I don't think I've answered your question. But
Kind of, let me try to explain it this way, I suppose. So you can use hyperbolic geometry to explain Euclidean geometry? Is that like a
no, not really.
Okay, so they're two separate. Okay,
so
that's
what convinced people, what I find the most convinced, so there were all these arguments when Gauss and the others said, we've made this new geometry. People would say, well, how do you know it's consistent internally? How do you know there isn't a contradiction out there? But these models I showed you, like this disk, that's a Euclidean picture, right? If you believe in Euclidean geometry, then you have to believe this setup I told you. You might say it's a bit funny, what I'm calling lines, but you have to agree that it works and it's consistent. So if you think Euclidean geometry is consistent, then you have to say hyperbolic geometry is consistent. And it took quite a long time, actually, about 50 years, for that to be sort of accepted, but there it is. So it's, and sort of, neither geometry is absolute. Space might be curved, but we sort of know how to work with it, and we can deal with it in whatever form it comes, depending on the context. Yeah.
Thank you.
Okay.
Yeah, 2 comments came in about the question whether there are computer games using hyperbolic geometry. There's apparently something called Hyperrogue and another one Hyperbolica. So they are out there.
Right.
They are out
Okay.
there. Here's another question. When stitching a hyperbolic plane together into a multi-hole torus, does the number of holes place any restriction on the hyperbolic structure?
No, because I showed you how to glue up an octagon to make a thing with 2 holes. If you want a thing with 3 holes, you take 12 sides. It's easy. So you take the number of holes and multiply by 4, and you can make one. Mm-hmm. And you can actually not just make one, but you can distort it. So I showed you a torus you got from gluing up a square. You could have taken a rectangle and made a slightly different shaped torus. You could take a parallelogram and make a different torus. And in the same way, you can make all different surfaces, ones with thin bits and ones with fat bits and so on. And that becomes a whole subject in itself.
Okay.
Yeah.
Okay, right. So this answers this question. Maybe another question from the audience? So when you mentioned Hamilton and the Quaternions, they came up very pleasantly in the talk. Is it known, or do you think that he knew about hyperbolic geometry, or?
That's a very good question, and I don't know the answer. I would suspect he'd heard rumors. By the time, you know, he died in, 1865, I believe? So I would have thought he would have heard rumors, but I don't know enough about his works.
Yes, right. So it might be interesting to
It could
look
be
into that.
interesting, and it could be that it was still a bit new and controversial at that time, I guess.
Yeah.
Whether it had got all the way to Dublin, you know. I don't know.
Yes.
There was another professor in this university who actually knew, and they were contemporaries. His name was James McCullough.
Oh yeah, I read about, yeah.
The guy who wrote Maxwell equations with zero effect.
Yeah, yeah.
So, in 1830s.
If you speak into the microphone, then people far away.
They were studying the light as something in ether. Remember, they wanted to describe Fresnel surfaces on propagation of light. So McCullough learned everything which was possible about this. And he was a good geometer, actually. They were together with Hamilton, and that guy definitely knew about hypergeometry.
Ah, yeah, because it's describing refraction.
Absolutely.
Yeah,
So
right.
Hamilton, they had some non-trivial relations, McCullough and Hamilton, but they were great, both of them. So I know for sure that McCullough worked on it and knew, and I'm very convinced that Hamilton also is.
Okay, thank you. So one final question before we have to wrap it up. Ben Mackay asks, are there any simple mechanical systems in the real world that can be modeled using motion inside hyperbolic surfaces?
I think it's a good question. I can't think of one. It's more like an idealized motion, but I mean, maybe you even know the answer to this. It may be possible to come up with such a system. The context I know about it in, it was as an idealized system in which you could have, you know, if you have an ordinary torus and you have a point moving around it in geodesic paths, it will go round and round and round, and then it will come back nearly on itself, and it just goes twisting round and round. It's called quasi-periodic. But in a hyperbolic surface, a typical path just goes everywhere. It wanders around. It's what's called ergodic. And it was very shocking to people that a path could kind of move around and come back on its crisscross the surface and fill out the whole surface. So I think it was more the inspiration that could happen, and then real-world systems were shown to behave in a way similar to that.
Right.
Yeah.
Okay,
Yeah,
great.
yeah.
I'm afraid we have to wrap it up now. Before we thank our speaker, of course, we have to also thank our sponsors of the Hamilton events. This is IBAC, the Irish Times, and Trinity College, which every year gives us this very nice auditorium. We are very grateful that you came over from England to Dublin this evening and gave us some glimpses into hyperbolic geometry and also some applications. Thank you very much.
Thank you.